Hello everyone. This video is an overview of linearization, a process for analyzing data and determining what the best fit function to the data is. So if we have a function that could be something like y equals mx plus b in math language, or y equals ax squared, or any number of various functions, y equals a times the square root of x. I would call this a linear function. This one a quadratic function. And this one a square root function. So it's worthwhile taking a second to think about what a function is. I read it as like a sentence. So like y is the output variable. And then everything on the right equals a list and operations that you do to the list. So by a list, I mean a set of numbers. A list of numbers, data, and then things that you would do to the numbers in order to get y, the output. So this is not anything new to you, I'm sure. Math class teaches you this, but in order to get the y list for a linear function, you multiply the x numbers by some number m, and then you add to that result some constant number b, and that'll give you the y's. And in order to get the y list for a quadratic function, one way to read this is, well, I take whatever numbers are in the x data set, square them, and multiply by a, etc., etc. So what we want to do when we linearize is take nonlinear data, some sort of curve, and we want to modify a list so that the nonlinear data plots as a line. The reason for that is multifold. There are several reasons. One, perhaps the biggest reason, is it's conclusive. It tells you what kind of function you've got in your data when you've got poor data, which happens a lot. Second reason is just linear functions are the easiest for most of us to understand. Okay, so when I say modify a list, that means raise the original data to a power. Raise the exponent to a different power than what it is. So, for instance, that could be square root. So that's the second power, sorry. Oops, square root, I said. That's the 1/2 power, or inverse. Take the inverse of the data. So that's the -1 power. So those are the kinds of things you're going to be doing to the data. Why are we doing this? Again, if you look at these three functions I chose at random, here I can put a fourth one here, y equals a over x, inverse. They are a kind of sentence that says, if I have a set of data of numbers x, real numbers, if I do this operation, it will give me another set of data that I know about y. I want to understand the data really well, so I want to be sure of what kind of function it is, and I also want to be able to interpret the function. We'll probably do interpretation later. So what we're doing is, what we want to do is either do to the x list what we think the function is doing, or I should say, we don't always know what the function is. What our guess of what the function is. Or undo to the y list, or the vertical list, or what's typically the dependent variable, but not always what the function is doing. Okay, so you that may or may not be helpful, but let's look at some examples from the College Board. Here is their graphical methods summary. So a constant function needs no linearization. It is a line. It's a horizontal line. Don't call it a straight line. All lines are straight, aren't they? It's a horizontal line. A proportional function also needs no linearization. It's a straight line with a slope, but no intercept. So this is like y equals x. Let's not say x. That was dumb. Y equals some constant. I used an a for a constant before. Could be capital A. In this case, it could be y equals ax, where a is 1 or some other number. And then this is our y equals mx plus b, which we've already discussed. No need to linearize that either. Their fourth function that the College Board gives us is an inverse function, inversely proportional. So y versus 1 over x. So what that's saying is if I have some numbers, x and y, let's make up some numbers that will work. We can't have 0, right? There's no 0, 0 there. We could have 1 and 1. We could have 2 and 1/2, 3 and 1/3, and 4 and 1/4. Okay, so there are my numbers. What I said was one way to linearize this is to do what to the data, to the x list, what you think the function is doing. So we know what this function is doing, but let's try it out. So if I modify this by saying x to the negative 1, I raised it to the power that I think the function, the guessed function, like I'm looking at this graph and I don't actually know that it's this. It just looks like this. Well, and these are my numbers, well, I'm going to take the inverse. This will be 1, this will be 1/2, 1/3, and 1/4. So notice that is definitely going to plot as a line. And that would work even if there were some constant. If it were not y equals 1 over x, but y equals 2 over x, some constant number in the denominator, or pardon me, in the numerator of the function, like y equals 2 over x. Okay, that's an inverse function. So I did to this what I guessed the function was doing. Okay, let's look at another one. Y versus x squared, same thing. Or, pardon me, x to the n. They give a general case, x to the n. That could be y versus x squared would be y versus ax squared, say. There could be a bx plus c, etc., etc. Or it could be y equals ax cubed, y equals ax fourth. Any whole number polynomial is what we're looking at here. Typically with one term if we're trying to linearize it. If it has more terms, it can't be linearized usually. But in AP Physics 1, we rarely see any polynomial of higher value than 2. Physics C mechanics, things like this are more common. Perhaps in Physics 2, there's something that's x to the fourth even. That's in the course. Okay, so what do we do here? Well, we guess that the function is raising x to the n. So to linearize this, you raise x to the n, your data list to the n, typically squared, both in Physics 1 and Physics C mechanics. Usually it's a quadratic function in most of our equations, but not always. It could also be, well, we'll come back to that later. It could also be a combination of different things. But so what am I saying? Well, I'll go back to my idea of made-up data. Let's see, this is for a quadratic. So I'll just make up some data where, let's say we had data that was really good, and it was x equals 2, or pardon me, x equals, it's early in the morning, y equals 2x squared. So then I could have 0, 0. 1 squared is 1 times 2, 2, 8, and then 3, 18. I can make up more points, but that's enough. So notice what happens if I go ahead and I see a curve. It looks like this. I got x and y. Oh, it looks like it could be a quadratic. That's my first guess. I'm going to square the x's because that's what the function is doing to the data. Well, look what happens if we look at what x squared versus y looks like. 0, 0 is a point again. 1 and 2 is a point again. 4 and 8. 9 and 18. Okay, well, what would this plot as? Looks like this would plot, if I plotted y versus x squared, I'd get a line with a slope of 2 because every number to the right in the y list is twice the x squared variable. So notice I didn't write x here, I wrote x squared because that's what we did to the data. And that's an example of raising something to a power when we suspect it's a power law, x squared, x cubed, x fourth. Square root function is a little different. We often do this, y squared versus x. There's a reason for that. It's related to what equations are on the AP equation sheet. But in this case, we undo, my bad, undo, I keep doing that. It's not always do, sometimes it's undo. Undo to the y list what we think the function is doing. Okay, so what's our example of that? Well, undo, if we've got a plot like this, and this is x, and this is y equals the square root of x, well, the function is taking the square root of x. To undo the square root, you square. So that's why we predict that y squared versus x will plot as a line. So what would that look like? Well, let's make up some numbers that'll work for this, and maybe it'll help you make sense of this. If it's the square root, well, 0, 0 works, 1, 1 works. See, 2, square root 2, that's not easy to think about without a calculator, etc. It's a decimal number. It's 1.414 or something like that. So let's do 4 and 2, and let's do 9 and 3, and let's do 16 and 4. Okay, so now we've got an example list of data where this is actually the square root of this vertical variable, y list, is actually the square root of the horizontal variable, the x list. So if I square y, what am I going to get? Well, 0, 0 again, 1, 1, 4, 4, 9, 9, and 16 and 16. Well, obviously that's going to plot as a line. And the same thing will happen if it were to be y equals some constant number times the square root of x. I think that's enough for this video, and in a later video I'll try to go over how do you interpret the line after you've processed the data and want to match it to something that happened in an experiment or a physical situation. I hope this is helpful. Remember, what one fool can understand, another can understand.